Okay, so now we'll talk about regularization, one of the favorite topic that I like to talk on. I will take around 10 to 15 minutes to complete something called as a regularization topic. And I think this is one of the most important topic in machine learning, or maybe you go to deep learning. Okay, so we'll learn about L1 norm, L1 and L2 regularization, which is often called a Rich and Lasso regularization. And I hope that you will understand that. And what is a regularization? So first of all, this is the problem that should come into mind, that what is and why regularization. I think these two questions must be your first question over here. So but before that, I'm going to highlight one something called as overfitting. And I think overfitting you all know, but just to those who forgotten about it, let's revisit that. So let's assume that you have an x and y plane, x here and y here. Okay, and here you have a data point. Okay, so you have a data point like this. Okay, and you fit it, and your model learns a lot. Your model learns a lot means your model is performing very best on the training set. Let's take an example that it performs, it is the error, the cost function over to here, means the residual error or the cost function over here will be approximately or very low to 0, and the accuracy on the training set will very high, because it tries to touch each and every point over here. Okay, and here your cost function means the difference between your predicted and the actual value, summation of I equals to 1 all the way around to the m will be approximately equals to 0. And if it is touching each and every point, so it's obvious that it is very best onto the training set on which it is trained. So it has learned a lot. But let's, for the sake of example, some example come over here. So what will happen? Your model will fail to generalize well onto the testing set. Okay, so that's why I'm telling that your model will fail to generalize well on testing set. So you can assume that this you can say that this model is on overfitting, because you find out that your model is performing a very best on a training set, and then if you evaluate it, then you will see that your model is performing very bad. Okay, so that's the sign of overfitting. So we always wanted to reduce the overfitting. So how can we reduce our overfitting? We have something called as a regularization, and how it happens, it can happen if you have a lot of features, or your polynomial degree is very high, if you're using polynomial regression. Okay, so the major cause of problem is lots of features. Okay, so now let's see how we can remove this, how we can prevent, or how we can make our model less prone to overfitting. So we have something called as regularization. Regularization will help you to eliminate the features which are less important. So again, I'm saying it will help you to eliminate the features which are less helpful or contains less information. Okay, so it will eliminate that. So that's what the regularization is doing. It is saying that if the feature is less important, remove that. Okay, or make their respective hyperparameter to be equals to 0. Okay, make the respective hyperparameter to be equals to 0 means make the respective, not a hyperparameter, make the respective theta to be 0. So we will see how what it will do. Just for as an example, let's assume that it will help you to eliminate the features which are less helpful. Now let's see how it will do. Okay, so let's assume that you're working on some problem which is house price prediction. Okay, so you're working on house price prediction, and there you have some features. So here you have x1, so maybe the size of the house, my favorite, size of the house, Okay, then x2 is maybe your favorite, the number of fans in a house, number of fans in a house. Okay, number of x3, maybe the number of bedrooms, number of bedrooms. Maybe another feature, number of maybe some fans is over, maybe ACs, okay, air conditioners. So here we have 4 features. Okay, and let's now what we'll do, so for each feature x1, x2, x3, x4, we'll be having some parameter weights, like theta 1 times x1 plus theta 2 times x2 plus theta 3 times x3 plus theta 4 times x4. And you can see over here that we have this is called the hypothesis function. So here these are the weights, these are the weights of these features, and we only have to learn these weights by just tweaking it. Okay, by just tweaking it. Tweaking means, let's take an example. I hope that you've already seen a linear regression. Just as an overview, that your theta was this equals to 2.1, theta 0 equals to 2.1 previously, and you just take out the partial derivative of your cost function with respect to this theta, and then you update the theta. Okay, why? And just see the linear regression part, all will be very clear. Okay, so here if you are being confused, please go to linear regression part. You will be not able to further continue, so please go back in linear regression if you're not able to understand what is theta and why it is. Okay, so this theta is a weight for the feature, and we can simply give, let's take an example that our theta 1 is equals to 2, theta 2 equals to 4, theta 3 equals to 2, okay, and theta 4 equals to 2. Okay, so we can simply multiply, so these thetas to be learned. Okay, so our user will give input. Let's take the size of the house, so 2 times size of the house, maybe 24 square feet plus then number of fans, so 4 times number of fans, maybe 4 plus number of bedrooms 2 times, because here we have theta 3 equals to 2. Let's assume that the user given 2 plus 2 times maybe number of ACs equals to 1. Okay, and this is the y hat of your model. So here you learn some weights, and usually you do the same. You have some parameter weights, which you learn by tweaking or by changing and taking a look if your model is performing best, and we just take out the partial derivative of our cost function with respect to this theta, and then see if our cost function decreasing. If it is, then we update the new theta, then we update our old theta with the new theta. Okay, so that's what we are doing over here, and I hope that you are understanding what I'm trying to say over here. So just for its intuitive examples, I hope that you understood what I'm trying to convey you over here. Okay, so let's assume that you have this. Now let's assume that this number of your model is overfitting. Okay, so what you do in regularization, you apply something called as ridge. So let's see the ridge regression, what it does. Ridge regression. Okay, so the equation for ridge regression is just add a regularization term at the end of the cost function. Okay, at the end of the cost function. So again, here we have theta 0 also. Here we have, oops, what happens? Here we have theta 0 also. Here we have theta 0 times x0, just a biased term, because an x0 is always equals to 1. Okay, so in ridge regression we add a regularization term. So here's what I mean. So j of theta equals to 1 over m plus I equals to 1 all the way down to the m, theta transpose xi minus yi squared plus, I'm saying plus, and here we have something called as learning rate, and this is just alpha. Okay, so don't assume that is a learning rate, this is just alpha. or you can say that someone can write it as a lambda. Okay, so it is just a Greek letter, just we didn't note. Okay, so don't compare with that learning rate alpha. Do not compare. Here I will tell you what is this, what this alpha does. 1 over 2 I equals to 1 all the way down to the m theta square I. Okay, so here we have added a new regularization term, a regularization term over here, a regularization term over here. So what is this? So this is simply what it does. It simply take the features which are less important and make that parameter weights closer and closer to 0. Okay, so what do I mean with this? So for an example, let's assume that the number of your model, using this equation, this is the L1 norm, it is the L1 norm. Okay, so let's assume, sorry, L2 norm, this is L2 norm. Okay, in ridge regression we have L2 norm, and here it's simply penalizing your theta, who is very less important. So let's assume that the number of AC or model find out that the number of AC is less important. So what it will do, so theta 4, our indicating the number of AC, the theta 4 is the weight of our number of AC, then it will make theta 4 to be closer and closer to 0, 0.000001. Okay, so it penalizes your theta. It penalizes your theta as it found that your number of AC is less important, so it penalizes your theta. And whenever you are multiply with penalize times the number of AC, then it will be also very means low. Okay, so that just helps you to less prone to overfitting. Okay, so it is not doing anything with your input value. It is doing, because if you multiply 0.00001 with whatever the number of feature, it will be approximately 0.00001. Okay, so like that. Okay, so what it does, it simply eliminates or penalizes your theta value by just making closer and closer to 0. Okay, so this is the L2 norm. Okay, and here we have something called as alpha, and alpha contains how harsh or how strict to be onto the certain feature. So let's assume that we have set some alpha. Obviously we don't touch alpha in scikit-learn, but here let's assume that your alpha controls the strictness. Okay, so if your alpha is large, I think so, if your alpha is large or lambda is large, some people may write this as a lambda also. Okay, so don't be confused. So if your lambda is large, then it will make it is making closer and closer to 0 now. It will make theta 4 equals to 0, fully 0. Okay, so it simply eliminates it. If you it is very strict if you keep this, it is very strict. Okay, so it controls the strictness. What I think. Okay, what I like to remember is controls the strictness. Okay, so and here you can see that you are taking the L1 norm and you are not taking of theta 0. You are explicitly doing for theta 0, because theta 0 is your bias term and you do not want to penalize your theta 0. Okay, so we are not penalizing, we are going from theta I equals to 1 all the way down to the m. We are not going to I equals to 0, we are going to each and every theta. Okay, so we are not going to theta 0, so we explicitly do for theta 0, and we explicitly tweak our theta, or we take out the derivative of our theta explicitly. Okay, because we don't want to penalize our bias it's our bias term. Okay, so this is the ridge regression. Okay, so we have something called as a lasso regression. Lasso regression means lasso regression is it uses L1 norm instead of L2 norm. It's just the same. It's also penalizes the theta value, but what it will do, I will tell you. Okay, so theta 0 equals to whatever your cost function will be. I'm just putting 1 2 3 plus, now I'm writing the regularization term, I equals to 1 all the way down to the m. You are not penalizing again theta 0, the norm of theta I. Okay, so this is what you, and here you are taking the L1 norm. Okay, so taking the norm, or you're taking the norm of your theta. Okay, so here here you are applying the L1 norm. So what it does, if the lasso regression is very strict, just assume it is very strict, whatever feature he finds, whatever I'm taking the gender as a he, okay, or whatever this lasso regression finds, whatever feature that less important he finds, he will directly make that theta 4 to 0. So here we assume, here we taken theta 4 equals to closer and closer to na, then in lasso it will take it directly to 0. Okay, so it is very harsh, so both have specific use cases. Okay, so these are this is called the L1 norm, and this is called the L2 norm. Okay, so here we have studied about regularization in detail, and I hope that you understood very clearly, and we have talked a lot. And there is one more, which is elastic net, which you don't need to worry about now. It's very kind of just combination of both of them, but it's not used in the industry as we use this L1 and L2 norm. Okay, so thank you for seeing this video about regularization, and you can head over to the next section to learn more about machine learning and completing this course. Okay, so thank you for seeing this video. Head over to the next section.